we now make a few introductory comments about Maxwell's equations, and then we'll discuss the issues of radiation pressure and momentum. But to start, okay, let's look at these equations. Now, Maxwell did not derive these equations. His main contribution as far as the equations themselves go was the inclusion of this term, which is the displacement current. Realizing that there had to be an analog for Faraday's law within Ampere's law. Okay, so here we have Gauss's law. Here we have Gauss's law for magnetism. Now, we didn't really go into a lot of depth with this equation. But there's a couple of things to note about it. Okay. So the difference between these two equations is that when I draw, and I just realized these are incorrect. These are A's. I got ahead of myself. Fluxes, yeah. So when you draw a Gaussian surface with area element dA around a charge, in principle, then you can calculate the electric field along the boundary of that area, right? So if I have an isolated charge, I can draw a Gaussian surface around it, a Gaussian sphere if you like, and I can calculate what the electric field is along the boundary of this sphere, at least in principle. Okay? So the entire point here is that if there is a net enclosed charge, then this can be viewed as a single monopole. So when you have flux coming out through a surface, that implies that there's a net of something within that surface. In this case, charge, and that charge is producing electric field. And so that charge can be thought of as a monopole. So a monopole is just an object with a single polarity. Now, in this case, it's electric polarity, right? It's either positive or negative. Gauss's law for magnetism implies no magnetic monopoles. So the entire issue is that so far as we have found, if I have a magnet, let's say a bar magnet, and I draw a Gaussian surface around that magnet, I will never measure any net flux through this surface. If this is a bar magnet, then we know this is a north pole and a south pole. And the magnetic fields are going to be these like butterfly loops, butterfly wing loops. And so what that means is whatever is going out of the Gaussian surface in one direction has to be coming back through in the other direction. And so there's no single pole producing magnetism. Okay? Now, this is a really, really deep point because there's a lot of theoretical work showing that magnetic monopoles could be possible. And there's theoretical work not only showing that that magnetic monopoles are possible, but some of the consequences for other physics if they exist. So, if you want to get a Nobel Prize, all you got to do is go get a magnetic monopole. Okay? If you can find and verify a magnetic monopole, you will get a Nobel Prize. But so far, nobody has ever found any evidence of a magnetic monopole, despite the fact that we think they should have been created in the early universe, right? So if we find some primordial magnetic monopoles, that would be really, really huge, because there's some pretty deep implications as far as the physics required for the aftermath of the Big Bang. But for the moment, we don't have any experimental or observational evidence for magnetic monopoles. So Gauss's law will hold, right? Gauss's law so far is true. But notice that both of these, okay, are fluxes, okay? So the first two of Maxwell's equations are both flux equations. And then the second two are line integrals. So first things first, you'll notice a pretty deep symmetry here, right? Here you have E dot dA, here you have B dot dA, here you have E dot dL, and here you have B dot dL. So the entire issue is, how do these fields behave around surfaces, and how do these fields behave around closed loops? Okay. Now, I should specify, when we say how these fields behave around surfaces, we mean closed surfaces. That's what this symbol in the integral means. It's a closed integral. You have to integrate over the entire surface, or you have to integrate over the entire path. So these are not just generic integrals. Even if your surfaces can be arbitrary and your loops can be arbitrary, the integrals themselves are not arbitrary, in that you need to be over a closed path or a closed surface in each case, right? So there's a really deep symmetry to Maxwell's equations, in that you have flux equations and you have line integral equations. And the fields are what you're integrating in both cases, okay? Then the other side of the equations are the things that cause those fields. In Gauss's law, it's the presence of electric charge. There is no flux through a arbitrary surface for magnetic fields, because there is no magnetic monopole, so whatever goes out must come back in. Faraday's law the line integral of your electric field. So what this is telling you is a time rate of change of magnetic fields will produce electric fields, and then you can calculate what the value of those electric fields are along some path. And then either steady electric currents or displacement currents, or both together, will produce magnetic fields. And you can calculate what the value of the magnetic field is along some loop. Okay, so you have flux and you have line integral equations. Okay, now, so here's the interesting thing. Well, here's a couple of interesting things. Number one, these four equations, then coupled with the Lorentz force law, okay. So Maxwell's equations are the first four. The bottom one is the Lorentz force law. And this is just a combination of the force on a charge in an electric field, F equals QE, and the force on a charge in a magnetic field, F equals Q V cross B. These five equations govern all known electricity and magnetism phenomena. Okay? These four equations as they're written here, govern electricity and magnetism in a vacuum. And when you apply electric and magnetic considerations inside matter, things change slightly, but the form of the equations doesn't, which is really super interesting. Okay, the bottom line is that the permeability and permittivity values change inside matter. Okay, so but the form of the equation stays the same, which is super interesting. Okay, so especially in vacuum, these 5 equations, as they're written, govern everything we know about electricity and magnetism. And so here's the question: what if we had a magnetic monopole? How would these equations change? Okay, well, first things first, let's call it QB for magnetic charge. Okay, the only 2 equations that would change are Gauss's law for magnetism and Faraday's law. So you'll note that Gauss's law and Gauss's law for magnetism are both your flux equations, once again. And so if there were such a thing as a magnetic monopole, then you would have some sort of flux that could be calculated. And it would look something like this. Okay, so whatever magnetic charge was enclosed, you could multiply that then by the magnetic constant, and that would be Gauss's law for magnetism now. What about Faraday's law? So notice that in Faraday's, well, if I compare Faraday's law and Ampere's law, both equations contain a time derivative of a flux. Faraday's law has the flux time derivative of the magnetic flux. Ampere's law has the time derivative of the electric flux. But what they don't have in common, and this is the stark break in the symmetry between both equations, there is no analog for regular current in Faraday's law. Okay, so magnetic current is not in Faraday's law, but what this symmetry is implying is if you had magnetic charge, magnetic monopoles, and you could make current with those poles, just like you make current with electrons, protons, you get them to move via some electric potential. You'd have to have some way of generating magnetic potential, but that's not a problem. We could actually do that. And then you could set magnetic monopoles into motion and you could get magnetic current. So if we had magnetic monopoles, we would have to adjust Gauss's law for magnetism like this, and then Faraday's law would look something like this. That's a really terrible E. Okay, so you'd have some sort of magnetic current term. All right. I don't remember how the epsilon and mu naught constants go, so don't quote me on this, but if I remember right, it would be something like this. Okay. Depending on what units you're in, you'd have to play the games with the epsilon naught, mu naught, get them arranged for all of the units to come out. But if I remember right, it's the current over epsilon naught. But in any case, um, your magnetic current would create electric fields, which is honestly really super interesting. So, that is just a little bit about Maxwell's equations and their symmetry. And we want to turn our attention now to the issue of momentum and radiation pressure. Okay, so imagine I have a beam of light. So the red represents my electric fields, and the blue represents my magnetic fields. Okay, and they're just oscillating and self-inducing one another, traveling to the right with speed c. And they're going to hit this surface. Okay. Well, so if electromagnetic fields are traveling energy, then they should also contain momentum. And by that fact, when a electromagnetic wave encounters a surface, it should impart momentum to that surface, and the surface should recoil. Okay, when once the light hits it. So if I kind of model this wave as just a beam of laser light, say, and it hits the surface should recoil at least slightly. And the higher intensity you make your beam, the more the recoil will occur. Right now, there's a spectrum between these two cases, but your two cases are where your surface could be a perfect absorber, or two, a perfect reflector. Okay. And things are going to behave a little bit differently depending on the situation. Now, if you think about it, this should make some sense. If the surface completely absorbs the light, like if it has a really nice matte black finish and it completely absorbs the light, then the recoil will be a little bit smaller. Whereas the perfect reflector should have a larger recoil. Now, why is that? Okay, so the idea is that for a perfect reflector, you then get a beam coming back. And so you have a higher change in momentum for the beam, but conservation of momentum says if the beam has a higher change in momentum, there has to be a higher change in momentum for the reflector. Okay? So you're going to get a larger recoil if it's perfectly reflecting as opposed to perfectly absorbing. But, okay, if this is going to experience a change in momentum, then that implies that it's going to experience a force. Okay? Because force is the time rate of change of momentum. And so the force that it experiences is going to be equal to the pressure that the electromagnetic wave exerts on it times the area of the reflector or absorber. Okay? But if we look at this equation, okay, pressure equals force per unit area. And if I multiply both of these by a unit of length, let's do it this way. Since we're in algebraic variables, let's suppose I have a length times a length. Okay? Well, the bottom area times a length is just a volume. And force times length is energy, or joules. But energy per unit volume is your energy density. Okay? So what this means is that for a perfect absorber, the pressure from radiation is equal to the energy density of the electromagnetic wave. But for the perfect reflector, if the momentum of the incoming beam is the same, okay, then because the beam experiences a double change in momentum, it has to experience, therefore, a twice as much pressure radiation. Okay? So, if you can calculate what the energy density is, then you can calculate how much pressure is going to be exerted on the object. But we can even go a step further. Okay? If we take the time average of these, then what we get for the time average, we can actually relate this to the intensity of the beam. Or the power per unit area. All right. And what we find is that if I take the time average of my pressure radiation, or I should say my radiation pressure, this equals the intensity divided by the speed of light. And for the perfect reflector, or I should say this is for the absorber, right? So this will correlate and this will correlate. So the pressure radiation pressure, said it again, in the reflector case, perfect reflector case, will be twice the intensity divided by the speed of light. And this comes from, once again, the time average calculation. And so if your radiation pressure is your energy density, from the previous discussion, remember that this is equal to, well, we should have it up here actually. Up here, yeah. So your pressure radiation, your energy density rather, is epsilon naught E squared or B squared over mu naught. And so let's say, for example, that we're using our typical sine wave, plane wave, So the oscillations of the electric field are in the I direction, but the propagation is in the Z direction. If I wanted to take the time average of this, then this would be the time average over one period of and we have our constant of epsilon naught out front. Okay, so this is the calculation of the time average. And your intensity is related to the square of your electric field. And so the maximum of your electric field comes out, since it's a constant, and the calculation itself gives you 1/2 T. Okay. And this is related to the intensity of your beam. Okay, so the intensity I is proportional to the square of the magnitude of the maximum electric field. And so your radiation pressure is therefore proportional to your energy density. Okay, and therefore that's why we can write these two equations down. And then the C comes in for unit purposes. Okay, but the upshot is that if you're given the intensities, then you can immediately calculate what the radiation pressures are going to be. Okay, so you actually don't have to go through this time average process. It's kind of built into the problem solving algorithm, if you will. Okay, so my recommendation, if you need to calculate radiation pressure, most of the time you're going to be given the intensities, and you can just use these formulas. If you're given the energy densities, then you can use these two formulas. Okay, one in the case of a perfect absorber, and the other in the case of the perfect reflector. Okay, and I really want to. I hope the point is driven home that because the light itself for a perfect reflector experiences a change in momentum of 2p in magnitude, as opposed to just p in the case of the perfect absorber, the recoil velocity of the or the recoil momentum of the surface is going to be much larger. Okay, now so there are applications to these kinds of things, right? So first, it was Maxwell who predicted that electromagnetic radiation should have momentum and therefore be subject to these kinds of processes. But there's a very interesting idea floating around the space exploration circles, and that is the use of a solar sail. So if I have a ship and I'm not going to be able to draw a spaceship really well, so we're going to go fifth grade here and just draw That's even terrible. I'm ashamed of myself. Let's see if we can't draw anything a little bit better. So here you have your rocket, or spacecraft, whatever the case may be. If you can unfurl a really large, really thin metallic plate, so most likely it would be like some sort of foil that would initially be folded up during launch, and then when you are out in space, it would unfurl. And if you are pointing away from the sun, then the sunlight is going to be coming this way, and the sunlight is going to hit the sail, and each individual beam of light from the sun that hits the sail imparts a little change in momentum to it, but the cumulative effect can be pretty extreme, especially over time. And so the idea being that if you don't want to use a lot of fuel to go into deeper space, let's say you want to send humans out to the moon of Saturn, Titan, or some of the moons of Uranus or Neptune, or you want to do some asteroid mining out in the Kuiper Belt, all sorts of things. It's really impractical to take the amount of fuel that it would require for a really, really large structure to support, all of the people that it would take to perform such an expedition. It would be really impractical to carry that much fuel. So the idea being, once you're out away from the Earth far enough and you can actually employ the sail, then the momentum from the light rays from the sun just continually impart impulse to the sail, and you're not going to accelerate very fast, but you will be constantly accelerating. Now, the rate of your acceleration will go down as the intensity of the sun diminishes, but your acceleration will always be positive because you'll always be getting positive delta P. And as a result, you can do this. If you could build the sail itself, you would be able to achieve really, really high speeds with very, very little cost of fuel. It'll take longer amount of time to get up to those speeds, but you don't have to carry as much fuel. So this is one idea for how to get spacecraft with larger amounts of people, requiring a larger spacecraft, into deeper space than we've ever sent people. Which, as we, a collective humans thinking about going to Mars or thinking about colonizing moons of Jupiter or Saturn or whatever the case may be, there are plenty of problems that we're going to have to overcome, fuel being one of them. And this is a really good, in principle anyway, practical way to save on fuel and get spacecraft into deeper space, right? So this is not just an academic thing. This is real technology that people are working on, so that in a few years this might be a viable solution. So that is a short discussion on Maxwell's equations and radiation pressure.